welcome you to the video, How do we conduct laboratory experiments effectively for experiential learning? I am Professor Jitesh Thakkar, Dean Academics and Professor Logistics and Supply Chain Management at Gati Shakti Vishwavidyalaya, Central University, India's first university in transportation and logistics sector. This is about my channel. Professor Dr. Jitesh Thakkar is the name of the channel, and it includes the playlist on faculty and student development, logistics, supply chain and infrastructure projects, and process excellence for manufacturing and service industry. About this playlist, faculty and student development. Faculty and student development is a multifaceted agenda, and this requires grooming on various aspects within the broader domain of teaching, research, and experiential learning. The aim of this platform is to address how faculty and student can respond to evolving educational needs and challenges in interdisciplinary scenario as expected by NEP 2020. This playlist shares critical insights on enhancing teaching effectiveness, promote research excellence and productivity, and enhance experiential learning. This platform explores critical dimensions of faculty and student development for enhancing the capability and quality of most important stakeholders of the higher education system, and that is faculty and students. About my university, Gati Shakti Vishwavidyalaya, it's a central university. It is India's first and only university in transportation and logistics sector, established by Ministry of Railways, Government of India. University has a unique mandate to contribute in the modes of transportation, including rail, road, aviation, water, ports, and shipping, with a focus on all three dimensions: technology, that is infrastructure, management, services, and policy regulations. University has established strategic collaborations both at national and international level with prestigious organizations such as St. Petersburg Transport University, Russia, Monash University, Australia, JTTRI, Lucchini, RS, SPA, Italy, Indian Defense Forces, Army, Air Force, Navy, Airbus, Jacobs, Nokia, Plaza India, Nippon Koi, and many others. The university operates with a unique vision in line with the expectations of 21st century, innovation-led and industry-driven. University offers variety of the programs in the School of Technology, within the School of Management for both regular students and working professionals. It offers the programs at the BTech level in engineering with a special focus on transportation, railways, MBA with a focus on logistics and supply chain and ports, MTech for working professional programs, intelligent transport system, railway engineering, roads and highway engineering, bridge and tunnel engineering, MBA in metro rail management, MBA in multimodal transportation, MBA in aviation and operations management, PhD in engineering and PhD in management for working professional with a focus on transportation and logistics sector. This video exchanges the views on how do we conduct laboratory experiments effectively for experiential learning. Let's try to have a deep dive into the topic and appreciate why experiential learning is important and in what way we can impart the experiential learning through laboratory experiments. So, experiential learning is all about learning by doing. I'm putting the learner into action mode, and here it experiences the spirit of learning by doing and gets deeper into connecting his theoretical conceptual knowledge with the practical applications. So broadly, this is realized through concrete experience where learner participates directly in an activity, whether it is a lab experiment, internship, field trip, simulation, community service project, or even a simple hands-on task. Reflective observation: after the experience, the learner takes time to reflect on what happened. And learner tries to inquire, what did I do? What happened? Why did it happen and way? That way. What did I learn? Subsequently, learner goes into abstract conceptualization. So from the reflection, the learner then tries to make sense of the experience. They connect it to the existing knowledge, theories, or concepts, and might form new understanding or ideas. This is where the doing transforms into knowing. And fourth important dimension, pillar of experiential learning, is active experimentation. So finally, learner applies their new understanding or conceptualization to new situation or further experiences. This might involve testing a new approach, trying a different strategy, or applying the learned lessons in a different context. And this cycle then continues, depending their learning. So experiential learning, which is learning by doing, involves four typical phases: concrete experience, reflective observation, abstract conceptualization, and active experimentation. So this is the typical experiential learning cycle, which provides the experience to the learner and immerse the learner into experiencing the utility of the concepts learned in the theory. So it provides deeper understanding, skill development, ability to transfer knowledge to real world problems. It goes beyond rote memorization by fostering critical thinking, problem solving, and more engaged and meaningful learning process. Let us look at today's AI era, artificial intelligence, and why experiential learning is essential for today's learner in the era of artificial intelligence. So let us look at where we are and what way we can leverage at one side AI, and on the other hand, we can get immersed into the artificial intelligence based experiential learning kind of experience. So experiential learning is becoming even more essential in the era of artificial intelligence because AI fundamentally shifts the skills demanded in the workforce. Typically, AI excels at automating repetitive tasks, rule-based tasks, data-intensive tasks, and this means that future jobs will increasingly require unique human capabilities which AI cannot replicate or replace easily. Experiential learning cultivates these soft skills and higher order thinking, typically critical thinking and problem solving. AI provides answers, but human needs to critically evaluate these answers, validate it, question it, and typically find the application, customize them for the suitable application. Second is creativity and innovation. While AI can generate content, true innovation, breakthrough ideas, and artistic expression remain human domains. So, experiential learning fosters creativity by allowing students to experiment, design, and build, often without a prescribed right answers. Third is collaboration and communication. So, experiential learning inherently involves teamwork, negotiation, and effective communication to achieve shared goals. The most important part is adaptability and lifelong learning. So, experiential learning instills a mindset of continuous learning, experimenting, learning through iterative process, resilience, and the ability to adapt to new tools and technologies. And this is something where at one side, when we are trying to take the advantage of AI tools, on the other side, we are developing some of the higher order skills in the learner, in the human being, which really creates unique opportunities in the professional world. So the question within the premise of this video is that what is laboratory experiment? Typically, a laboratory experiment is a research method conducted in a highly controlled environment, often but not always a physical laboratory, and the primary goal is to establish a cause and effect relationship between variables. I have at one side independent variables, and I would like to manipulate with the independent variables that may be the different kind of parameters. And as a researcher, experimentalist, I want to actively see what happens to the dependent variable when the independent variables are changed. On the other hand, I am interested in the measurement of the dependent variable and the effect of the manipulation in the independent variable, what effect it brings in my dependent variable, and that is where I am trying to define the entire premise of my laboratory experiment. So the going further and taking the greater drive in our video, how laboratory experiments impart experiential learning. Specifically, we want to connect these two important dimensions, and then we want to structure how can we really organize our experiments which ensures the experiential learning. So typically, my laboratory experience must move students beyond passive reception of information to active engagement and discovery. It should create the interest in the learner, and learner should feel motivated to verify the theories, to verify the concepts they have learned during their regular theory classes. So typically, the purpose is to provide hands-on application of theory. Students don't just read about chemical reactions, they perform them and observe the changes firsthand. Second, deeper understanding and retention. Students engage multiple senses: sight, touch, smell, cognitive processes, and this kind of hands-on multi-sensory experience makes the learning more concrete, long-lasting, memorable, and deeper. The third important thing is development of critical thinking and problem-solving skills. So when, as a learner, I conduct the experiments, I realize that there are many other extraneous or external factors that are affecting my experiment, and experiments are prone to errors, certain kind of biases. So experiments rarely go perfectly as planned, and this necessitates critical thinking to identify errors, analyze unexpected results, troubleshoot the problems, and this iterative process helps me to formulate the hypothesis, revisit my hypothesis, design procedures, collect and interpret data, and draw evidences based on conclusions and verify these conclusions with the existing body of knowledge. And if there is any significant deviation, I can go back to my experimental setup and once again iterate. So this kind of iterative process helps the learner to take a deep dive into the understanding, and this understanding becomes long lasting in the memory of the learner. In addition to this, experiments provides experiential learning because it fosters curiosity and inquiry. It ignites curiosity. Typically, when students they observe the outcomes, they are encouraged to ask why this has happened, what if. Practical skill development: when you prepare the experimental setup, when you follow the safety protocol, record observations accurately, document your observation, write the reports, follow the procedures. Actually, it is preparing you for typical engineering field jobs or professional jobs. And this kind of exposure one can only derive while conducting the experiments in the laboratory. It fosters collaborations and improves the communication. Basically, it is the group-based approach. You conduct the experiments in a group, requiring students to collaborate, communicate effectively, share ideas, resolve disagreements, and all this develops teamwork, interpersonal skills, which is very crucial for future academic and professional success. So, putting together, laboratory experiments are a cornerstone of experiential learning because they provide a rich, interactive environment where students can experience, reflect, conceptualize, and actively experiment, leading to a more robust and meaningful learning journey. So, let us go further in our exploration on the topic how experimentation can provide experiential learning. And now let us try to see how should laboratory experiments be conducted in step-by-step manner for extracting maximum experiential learning. As we have seen that the experiential learning cycle revolves around four most important concepts. It is concrete experience, having the actual experience, reflective observation, I reflect what I did, why I did, abstract conceptualization, learning from the experiences, and then active experimentation, trying out what you have learned, and you try to extend your learning to other segments. So this is the full cycle. Now let us try to see in what way I can conduct the laboratory experiment step by step, phase by phase manner so that I can ensure the experience of all four components, which are the four pillars of experiential learning. So let us look at the phase one. And phase one is about preparation. Here you are setting the stage for concrete experience and initial reflection. Define clear learning outcomes. What specific knowledge, skills, and attitudes should student gain from this experiment? I'm not conducting experiment just to derive some results, but I have a strong logic for developing set of competencies in the future professionals. How does it connect to broader course concepts, real world applications? So student will be able to identify factors affecting reaction rates, develop safe lab practices, will learn to interpret experimental data, and they will draw the conclusions about a specific scientific principle. So my first phase focuses on preparation, that is define clear learning objectives. There are certain important things that are to be considered as pre-lab engagement, pre-thinking, and active prior knowledge. This includes provide context and purpose. You motivate your learner why you are doing this experiment, what is the theory behind, what are the principles you are really trying to test, and don't just give them a procedure. Hypothesis formulation, encourage the students to formulate their own hypothesis. What exactly they want to verify? Hypothesis is an assertion, it's my assumption. And typically, what prediction or assumption I want to verify through this particular experiment or conducting this experiment. Pre-lab questions and tasks. You assign some readings, videos, or short quizzes to ensure students have the necessary background knowledge, curiosity, motivation, and really take a critical experimentation with necessary background and motivation during the laboratory hours. Safety briefing, thoroughly review all safety procedures because it's not just an experiment, you are preparing them for the future professional jobs, and let them understand when they are in the workshop, they are in the laboratory of any kind, mechanical engineering, electrical engineering, physics, or chemistry, what kind of safety protocols to be followed to prevent potential hazards and emergency situations. What are the protocols? Phase 2 is the execution, and typically, as per our experiential learning cycle, we call this as concrete experience. So once in phase 1, you have provided the background, your learner is adequately motivated, he has understood the purpose of the laboratory experiment, and now in the execution phase, he is well prepared to follow your procedure. And this is the concrete experience phase. Hands-on experimentation, you allow for active participation. So students should be actively performing, and this is something where you should decide about your batch size and see that you have adequate number of experimental setup present, or adequate number of students should be allocated for a particular experimental setup so that they have opportunity to experience hands-on in the laboratory. So they make the observations, collect the data themselves. All this is part of active participation. Embrace productive struggle. You resist the urge to jump in and solve every problem for them. Yes, you are a facilitator when students are engaged into experimentation in the laboratory, but don't try to put them under a stereotype kind of procedural framework where they do not iterate, they do not feel motivated to experiment. Let them grapple with challenges, troubleshoot issues, and learn from mistakes. Offer guiding questions instead of direct answers. Promote collaborations. Encourage students to work together, discuss observations, and share responsibilities within the group. And emphasis on observation and data collection. So you stress the importance of accurate and detailed observations, both qualitative and quantitative. It's not just what numbers they are collecting, but they should also internalize some of the important observations, qualitative insights, and this guide them for appropriate recording of the data, and you can help them by providing appropriate data recording techniques. Phase 3 includes post-experiment. Now students have conducted the experiment and they are in the phase 3. Typically, as per our experiential learning cycle, it is called reflective observation and abstract conceptualization. And this is very important phase because now you have collected the data, you have conducted the experiment, and you can only internalize if you really reflect on it. So immediate debriefing or the reflection is the third phase, and you facilitate the discussion as an instructor. Reflective observation. So immediately after the experiment or design poses, lead a question discussion like, what did you observe? Let learner to express. Did your result match your predictions? Why or why not? They would have some idea conceptualized, conceived in the phase 1, and now it's time for them to reflect. What went well? What challenges did you face? What surprised you? What data did you collect and what does it tell you? Journaling, lab notebooks. You encourage the students to record their reflections on data, on observations, on conducting the experimentation, insights, and questions in their lab notebook. And this helps them to process their experiences. So data analysis and interpretation, that is the abstract conceptualization. It is a kind of guided analysis. You organize the data, analyze, interpret the collected data. You can put graphical representation, conduct statistical analysis, identify patterns. You connect it to the theory. How does what you observe here illustrate the concept X or concept Y, whether you are working on fluid mechanics or strength of material, whatever concept you are trying to investigate, how does what you observe really relate to the framework or the concept you are trying to appreciate? Then formulating the conclusions. It's also very important to have error analysis and further questions. This is the part of reflections, but I would call it a deeper reflection. So you try to identify the sources. So you have the theoretically ideal graph of your results, and now you have conducted the experiment. You may realize the difference between these two, and you try to tap source of errors or why there is a deviation. So encourage students to critically evaluate their methods and identify potential source of experimental error. Not necessary that all the deviations are because of error, but yes, you try to find out whether there is an effect of extraneous factors, there is a problem in the experimental setup, or there is a measurement error. You try to figure out. So this develops their understanding of scientific rigor and generate new questions like what next? What if? Suppose I would have manipulated Y parameter compared to X, then how my results would have been different. So this fosters curiosity and a spirit of ongoing inquiry. When we come to phase 4, that is application and extension, and I would call it as a part of our experiential learning cycle, active experimentation. This fourth phase typically involves reporting and communication, lab reports. You provide them a structure. I will also discuss about the structure of lab report. And the structure should go beyond just a procedural recount. They should include introduction, hypothesis, methods, result. Your learner should get 360-degree feel about what, why, how, when, and for what purpose this experiment is conducted. Presentation and poster have students present their findings to their peers, fostering communication and critical evaluation skills. You extend this application and extension through application to new scenarios. It can include problem-solving tasks, assign follow-up problems or case studies. Now you have conducted the experiment in fluid mechanics or design or robotics. And now this is the case situation. To what extent your results are applicable or how you can really differentiate the context and what modifications might be required if you have to conduct your experiment again. Design challenges ask them to design a new experiment. As I mentioned, suppose if there is a new situation, that what modification you would like to do in your experimentation and how you will modify your hypothesis, or you would try to solve a similar problem. Real world connection discuss how the principles learned in the lab apply to real world phenomena, industries, or societal issues. This is extremely important, and many a times learners have a disconnect and they are not able to really see the real utility of their experimentation for the variety of societal issues, which is the ultimate goal resolving such issues is the ultimate goal of any science, of any engineering. For example, there is a flood-like situation, there is an earthquake, there is a natural calamity. There can be different kind of crisis situations, stampede. What way your technology, your experimentation, your learning will really help this kind of situation to manage, handle better. So you are trying to extend your learning to the larger context as a part of phase 4. Let us try to experience all these important phases with the experimental, say, setup and the commonly known experiment determination of tensile properties using a tensile test. So in general, all the engineering first year, they conduct this experiment. And let's try to see that if I have to conduct this experiment, then how can I help my learners to experience the process of experiential learning and how they can conduct this experiment in a step-by-step, phase-by-phase manner systematically. So the experiment on tensile test, the purpose is to determine the material's behavior under tension, including its ability to withstand stretching and deformation before failure. You can see the graph and you have the gauge region indicated between AB and CD. So when elongation takes place, the necking will form, and typically you can measure the yield strength, you have the plastic deformation phase, you have the elastic phase, and then you have uniform elongation, deformation, and you can also measure the total elongation at the fracture. So the procedure is a specimen is clamped and pulled until it breaks. Load and elongation are measured to create stress strain curve, and you want to measure some of the key properties: yield strength, tensile strength, elongation, modulus of elasticity. So let us see how we can really conduct this experiment in the laboratory in a step-by-step, phase-by-phase manner. So overall goal is to understand the mechanical properties of the materials, strength, ductility to a tensile test, and to apply and interpret engineering stress strain curve. So I can begin with phase 1. That is the preparation phase, setting the stage for concrete experience and initial reflection. So I would define clear learning outcomes. And I'm just trying to put it in terms of a couple of parameters. My learning outcomes, first is the knowledge that learners should gain through this experiment. Students should be able to define and calculate engineering stress, engineering strain, Young's modulus or modulus of elasticity, yield strength, ultimate tensile strength, fracture strength, percentage elongation, and percentage reduction in area. What skills I want my learners, students to develop? Students should be able to safely operate a universal testing machine, UTM, for a tensile test, accurately measure specimen dimensions, typically your elongation, the diameter, interpret load displacement data, and construct an engineering stress strain curve. What kind of attitudes I want to develop in my learners? Student will appreciate the importance of material properties in engineering, design, and develop a critical approach to experimental data. Again, as a part of phase 1, I will try to create sufficient background which can not only equip my students, but put them under critical thinking and motivation for conducting this experiment. So as a part of Point two, pre-lab engagement, that is pre-thinking and activating prior knowledge. I will try to define the context and purpose. As an instructor, I may try to postulate the entire problem as imagine you are designing a bridge, an airplane wing, or even a simple paper clip. Why is it crucial to know how strong material is? What may happen? What happens if it stretches too much or breaks under the load? So today I will say we will perform a fundamental test that engineers use to characterize how materials behave under tension. And this is something where I'm setting the pitch for my experimentation, that is the tensile test. Discussion: what do you think happens to a material when you pull it? Do all materials behave the same way? Give examples. So if you have the ductile material, if you have the brittle material, mild steel, aluminium, what may happen? So hypothesis formulation may go, as an instructor, I would say, for the material we are testing today, maybe mild steel or aluminium, what kind of stress strain curve do you predict it will have? Let them think. Do not give them the ready-made solution. Will it stretch a lot or break suddenly? Will it have a clear yield point? And student can just sketch their predictive curves. You are not trying to ask them to reproduce what is given in the textbook. Let them imagine. We are immersing them into the experiential learning through laboratory experimentation to see that they foster, that their critical thinking is fostered, and they develop the ability to imagine and subsequently validate their imaginations. Question you may raise, based on your everyday experience, which material do you think would stretch more, a rubber band or a steel wire of the same thickness? Let them create the curiosity. Couple of questions I may like to consider as pre-lab questions or tasks. Here you may direct their inquiry to a little bit the concept. Now, as you are proceeding towards conducting experiment, so read section on stress strain, elastic deformation, plastic deformation, and key tensile properties. It may be a kind of revision for them. Ideally, student should conduct the experiment once they have created some theoretical base, and you provide them some reading material or some preliminary instruction, and this may include for tensile stress experiment, Young's modulus, yield strength, UTS, etc. from the textbook, notebook, or maybe the manuals of the universal tensile setup. Watch a short video demonstrating a tensile test. This would really benefit them because now they have imagined something. Let them also further strengthen their imagination. Complete a pre-lab quiz covering definition, basic calculation. Just try to see are they ready for the experiment or not. Like what is stress, force upon area, and safety procedures, and so on. Familiarize the learner with the parts of the universal testing machine. Let them also appreciate, because ultimately UTM, Universal Testing Machine, is an outcome of sound engineering, rigorous engineering. Let them also appreciate that what kind of precision manufacturing, what kind of assembly, what kind of meticulousness has gone into when this machine is designed and manufactured. Safety briefing, thorough review of UTM safety protocols, keeping hands clear of moving parts, using safety guards, understanding emergency stop, and so on. Because tomorrow when these professionals, they will go to the field, they need to observe and enforce this kind of safety protocols to the workforce. And they need to be adequately sensitized right at the laboratory stage for safety protocols. Discussion on the hazards of breaking specimens, maybe flying fragments, sudden release of energy, proper use of PPE, personal protective equipment, safety glasses, closed toe shoe. You try to sensitize them. The third important point within the phase 1 is experimental design, that is the structured inquiry. Here as an instructor, you provide the material samples, mild steel, aluminum, universal testing machine and basic instruction for setting up the specimen. Students here at this stage will be responsible for precisely measuring the initial gauge length, diameter of their specific specimen using appropriate measuring tools. It may be vernier caliper, micrometer. Understanding why these measurements are critical for calculating stress and strain. They prepare the data tables for recording load and corresponding displacement readings. Optional maybe for slightly more advanced, deciding on the appropriate data collection intervals or auto logging setting on the UTM software. Now let us go to phase 2. So in phase 1, we have prepared our learner with necessary concepts, curiosity and motivation to go further and conduct the experiment. And this phase 2 execution, is related to the concrete experience of experiential learning cycle. As a part of this, the fourth point, I will go for the hands-on experimentation. So the first thing that you expect your students to do is specimen preparation and mounting. So students under supervision will carefully measure the initial dimensions of their assigned specimen. They will learn how to properly secure the specimen into the grips of the UTM, ensuring it is aligned correctly. And then machine operation, one student or rotation basis operates the UTM under strict instructor guidance, apply tensile load gradually. Please allow your student to have hands-on experience. Experiential learning is all about learning by doing. It's an action-oriented learning. Other group may actively observe their specimen behavior, initial elastic deformation, necking, eventual fracture, as we do in the tensile test experiment. As a part of phase 2, then you move to the data collection. Students are expected to record the load and corresponding displacement values, either manually at specific interval or by monitoring the data logging system. They should note down the ultimate load and fracture load, and crucially, they observe and note visual changes in the specimen. This could be elastic elongation, return to the original length upon unloading, onset of plastic deformation, permanent deformation, necking, localized reduction in cross-sectional area, and 4, as you have seen in the stress strain diagram, fracture point. Continuing, observation and discussion during the test. So when your experimentation is going on, you can pose some question to further nurture and induce the curiosity. As an instructor, you may say, look at how the material is deforming. What do you notice happening to its diameter? Is it deforming uniformly? Student may try to respond, it's getting thinner here, it's just made a weird pop sound, or but didn't break, and whatever. Post-fracture measurement. After the specimen fracture, student carefully remove the 2 broken pieces. They measure the final gauge length and final diameter at the fracture surface. Now, let us go into the phase 3, and this is post-experiment. So once again, revisiting phase 1, I prepared the student, induced them with enough motivation and curiosity. Phase 2, I conducted the experimentation, and now phase 3, it is the post-experiment. reflective observation and abstract conceptualization as a part of my experiential learning cycle. So point number 5, as a part of phase 3, is immediate debrief and reflection. You initiate the group discussion. What happened? So you may pose a couple of questions. Describe what you saw during the test from start to fracture. Did this specimen behave as you expected? Where did your hypothesis match or differ from reality? What did the load displacement curve on the screen tell you about the material? There can be surprises or challenges, and you may pose like this. Was there anything surprising about the way material fractured? Example, cup and cone fracture for ductile material, which is usually expected. Flat fractures for brittle materials. Did you encounter any challenges during measurement or machine operation? How did you overcome them? Initial interpretations may follow, and you may say that based on what you saw, was the material more ductile or more brittle, and how do you know? So as a part of phase 3, you are putting your learner into the reflective observations and abstract conceptualization. As a part of phase 3, you conduct the data analysis and interpretation, that is again abstract conceptualization. So your calculation would follow. Students would calculate engineering stress, that is sigma is equal to load upon initial area, engineering stress delta L divided by initial gauge length for all recorded data points. They can calculate the percentage elongation. So initial gauge length minus final gauge length divided by initial gauge length into 100%. Calculate percentage reduction in area, that is initial area minus final area divided by initial area. Graphing, they can plot the engineering stress strain curve using their calculated data. This can be done using the software or Excel or manually. Going further, identification of creep properties. So now students have plotted the curve and they can identify and calculate Young's modulus, slope of the linear elastic region, yield strength, using the 0.2% offset method as generally we use for materials without a distinct yield point, or directly for material with a very clear yield. Ultimate tensile strength, maximum stress on the curve, and fracture strength, stress at the point of the fracture. How do you connect it to the theory? So instructor may pose a question. Compare your calculated Young's modulus with theoretical values for your material. What does this modulus tell you about the material stiffness? And the discussion may be initiated. How do the percentage elongation and percentage reduction in area quantitatively describe the ductility or brittleness you observe qualitatively during the test? Where on your stress strain diagram do you see the transition from elastic to plastic deformation, and what does this mean for the material? So many interesting questions you can pose, and learner really would feel motivated to think critically on their experimentation and the utility of the experimentation for the larger application. Point 7, you can put them into the deeper reflection by expecting them to conduct error analysis, addressing some of the advanced questions. So maybe the sources of error, what were potential sources of error in your experiment? Do you think there can be measurement inaccuracies, machine calibration, gripping issues, specimen imperfection, and how might these errors have affected your results? Let them reflect on the error component. Some more questions for deeper inquiry can even be initiated. How would the stress strain curve change if we tested a ceramic or polymer instead of a metal? Let them search on net or in the textbook or wherever, and then create the curiosity that what may happen if my specimen is of ceramic or polymer? What if the temperature change during the test? You are just conducting the experiment under the normal room temperature condition, but if you apply the higher temperature, what may happen to the test? How might manufacturing processes affect the mechanical properties we measured? So maybe when you manufacture some component, some kind of imperfection movement may take place, and because of this, the mechanical properties directly get affected if you conduct the experiment for the specimen which has come through different kind of manufacturing processes. Then there may be difference in the final result. Let them think, what would a compressive test look like and how might the results differ? So there are many questions you can pose through which your learner will have the deeper reflection and will feel motivated to extract the maximum value of the laboratory experiment. Again, as a part of phase 4, point number 9, application to new scenario. We are not just stopping at the error analysis or extensive inquiry. We are trying to extend the results to the applications, to the new scenarios. For example, as an instructor, you may express, you are an engineer designing a structural component for a robotic arm, and typically this arm needs to withstand a specific maximum tensile load without permanently deforming. Now, if you are given this situation and 3 different materials with unknown tensile properties, which one would you choose based on the data you could gather from a tensile test and why? Student would use their understanding of the yield strength and then they will try to select an appropriate material for the application of robotic arm. You may put them into case study analysis. You may ask them to analyze the real world material failure case study. For example, many a times we come across in news that bridges have collapsed, a broken component, failure, mechanical failure in the aircraft. And through this case study, you try to discuss how understanding tensile properties could have prevented it. You can also put them into the comparative analysis. You provide the students with tensile test data from different materials, let it be cast iron, a high strength alloy, and then you can ask them to compare and contrast their properties based on the curves, relating them to the potential applications. So this is all we have done up to phase 3, and now let us move to the phase 4 for the experiment tensile test. And phase 4 is about the 4th phase of my experiential learning cycle, and that is experimentation, applications and extension. Here, learner would report and communicate. So formal lab report, which typically includes the introduction, purpose of the experiment, background on tensile testing, material property, hypothesis, initial preconditions, materials and methods, the specimen, equipment, procedure, results, raw data, graphs, calculated values, discussion, interpretation of the results, comparison with theoretical values, explanation of the observed behavior, necking, fracture type, and so on. And conclusion, summary of the finding and what was learned. Subsequently, let it followed by group presentation. It can be optional but recommended. Groups present their findings to the class and let them defend their interpretation and answer the questions their peers are raising. So when it comes to reporting your experimentation results, a good outstanding laboratory report should ensure a couple of important dimensions. First is the clarity and consciousness. There should not be any ambiguity. It should be to the point, free from jargons, accuracy and precision in terms of data collection, calculations, observation, recording, completeness, all necessary informations, assumptions, your mathematical formulations, your data recording, interpretations, persons involved, everything should be provided. Logical flow and organization. So obviously, as I mentioned, introduction to conclusion, it should follow the logical flow. Critical analysis. This is the key differentiator. It's not just enough to present results. You interpret them, link it with the applications. Proper scientific tone. Do not use personal pronouns like I, we. Maintain a formal academic style. Effective visuals. Wherever you have recorded the data, try to present your data through tables, graphs, diagrams, which can provide much better visual appeal and interpretation. Referencing, proper citation of all external sources, textbook, articles, manuals that demonstrates your academic integrity. Understanding of the underlying principles. Now you have interpreted the results. How do you relate it with the underlying principles and your error analysis? So I'm just presenting the broader structure that a good, outstanding lab report should follow. So begin with the title page. Title of experiment. It should be concise, descriptive, informative, like determination of mechanical properties of milestone via tensile testing. You put your name so that your report can be appropriately evaluated, your partner's names, group members, course name, number, instructor's name, date submitted. Number 2 is the abstract or executive summary. It provides the brief, self-contained summary in about 150 to 250 words, which includes the purpose of the experiment, methodology followed, key findings and results, not in detail, but just the key findings. For example, tensile test reveal that the milestone specimen exhibited a young modulus of X GPa gigapascal and a yield strength of Y MPa, demonstrating ductile behavior and so on. State the most important conclusions drawn and write this section last after the rest of the report is complete. Third important section in your laboratory report is introduction. You put background, theoretical context, principles, laws, purpose and objective, what questions you are trying to answer, what principles are you trying to demonstrate, the objective of this experiment, the hypothesis. So you may say here, for the tensile test experiment, it was hypothesized that the milestone would exhibit a distinct yield point and ductile fracture characterized by significant plastic deformation before failure. Section 4, materials and methods. The procedure, experimental procedure you followed. You try to list all significant materials, chemicals, specification of the UTM, your universal testing machine, and your milestone cylindrical specimen, whatever it may be, 10 mm diameter, 50 mm gauge length, and you describe the procedure, how this experiment would be conducted. So you use clear and concise and active passive voice, include any specific setting parameters, calibration steps, relevant safety precautions, and so on. Number 5 is results, presentation of data. As I mentioned, you try to put raw data in the tabular format, load versus displacement reading, for example, tensile test. Process data include tables of calculated data, engineering stress versus engineering strain, visual representations using graphs, charts, figures, and then you provide the descriptive summary where you are trying to briefly describe your key findings from the data, what behaviors you have observed. So, for example, you may say that the stress strain curve for milestone exhibited a linear elastic region up to the maximum 250 megapascal, followed by a distinct yield point and subsequently plastic deformation. Necking was observed visually at an engineering strain of approximately 0.15 and so on. Subsequently, your sixth section in your report is the discussion where you are interpreting your results against your purpose, hypothesis. How do you connect your findings with the scientific principles you introduce in the introduction, and specifically refer you can data, graphs, tables to support your point. For example, the calculated Young's modulus of X gigapascal aligns closely with published values for mild steel, conforming the material's elastic stiffness. Comparison to expected results, literature, did you result? Your result support your hypothesis, if not why, compare your results to the theoretical predictions, accepted values, and so on. And subsequently, as I mentioned, you report your error analysis. So it could be both systematic error and random error. There are some chance causes, you don't have much control over it. But yes, if there are systematic causes and you find significant deviation from the expected results, then you can cite the reasons for that, and if required, you may conduct the experiment again. You cite the limitations of your experiment, discuss any limitations your experimental design or methodology had, implications, significance, why these results are important, what practical problems you can address with this experimentation, and suggestions for future work. The last section, 7, is the conclusion where you are summarizing your key findings. You restate purpose, outcome, you reiterate whether the experiment's objective was met or not, and broader significance, maybe for a societal context or a critical problem in the external world. References and appendices is optional. If required, you can put. So this will complete your report with total 9 sections. I am also presenting graphically how your report should look like. So A1 is the title, A2 is the abstract, A3 is the table of content, A4 is the introduction, background theory, purpose, and so on. A5 is the methods, experimental, overview, apparatus, equipment table. A6 is the results. You narrate like a story, tables and graphs, equations in variables, uncertainties, discussion, then references, and this makes your lab report complete. So finally, having appreciated how to conduct laboratory experiment to impart experiential learning, it is extremely important to understand the role of lab instructor and what characteristic a lab instructor should possess. So a great lab instructor must exhibit some of the personality traits. Number 1, help students understand importance of the day's activities by clearly explaining the activities significance, what kind of experimentation they would be performing, what is its important. Provide specific and clear instruction, don't confuse them. So for that, you should be prepared, ready before you really engage student in the laboratory. Prompt student to recall prior knowledge, ensure students have required prerequisite knowledge so that they can really appreciate the experimentation and ensure that they got immersed into experiential learning. Make practical problems and experiments relevant. Turn experiments into practical problem solving exercise and prepare students to work collaboratively, teamwork with specific roles, and find balance between offering just enough help and forcing students to solve problem on their own. This is very important. It's not just I will throw the problem and leave the students on their own. I am a facilitator in the lab and I will try to see that students get the trail. When they are putting the effort, they should feel confident and they should proceed step by step in a creative, confident manner so that they reach to the ultimate objective of the experiment, internalize the overall procedure thoroughly. Thank you for your interest in learning the various dimensions of faculty and student development. We will keep exploring more issues through this platform for the benefit of faculty and students, most critical entity in the higher education in India. Thank you.